continue talking about magnetism. So we've introduced magnetism. Magnetism will not be covered on the test next week. This stuff is, right, so everything up through the capacitors and the transient circuits with capacitors, that will be on the test. This will not be on the test. I was worried when I see that. It's supposed to be pretty close. Safe though, right? So magnetism, let's dive into it. Strong magnets are called ferromagnets. Ferro coming from the Latin word for iron. Iron is not the only magnetic material, but not all materials are magnetic. So for instance, here's some nice strong neodymium magnets. I like to keep them together like this because they're too brittle for their magnetic strength. So if you take them apart and let go, they will fall together and break. So we used to have twice as many. But if I take this and I bring it to different things, there's no attraction to, I'm pretty sure this is metal, but there's no attraction to that metal. Or I can take, my keys are on a thing that is metal. Here's some aluminum. No attraction. Aluminum is not magnetic. On the other hand, the iron screw is magnetic. So some materials are ferromagnetic, strong magnetism. Some are not. And with the strong magnets, you can do cool things. I don't know if you guys have seen the fun magic tricks that people do, but here's one of my favorite lame magic tricks that I don't know how people get away with it, but I've seen people on TV doing this and everyone's all, ooh. So I'll go over here. I'll go to this table. Chad's not here. You put the magnet on top here, and then you slightly have, oh boy, world, that's what, I get away from the drawer. You slightly put the magnet underneath here, and you move it around. You see the magnet just moves over, and you have to have a way of moving it so people can't tell you're moving stuff around. But you can move it around, and people think, woo, magic! And did you notice what happened when I first brought it up? It jumped. Switched poles. It switched poles because we have the rules that opposites attract and likes repel. And so you can do other cool things like, I'll bring this here, and I'll bring it down. Now these are sets of the poles, if I remember right, are repelling. What? So not only did it pull it up, but what did it do first? It flipped it, which is really cool, right? Now if I had it set this way, it wouldn't do anything cool. It would just come up without flipping. But when you have it upside down, it flips it because the magnetic field lines are coming out and around, and the magnetic force is such to try to make the field lines go into the south and out of the north. And so the field lines are going to interact. Now, notice I'm already talking about field lines like there's something real. We talk about field lines like there's something real all the time. But in fact, what are they?
A model that we use to predict behavior.
Okay, a model that we use. That we call them lines of force, right? They're a force field that we can then use to calculate what the force is going to be on something. So they're totally fun to play with. Iron is a well-known ferromagnet, but other things include nickel, cobalt, chromium dioxide. So when I was a kid, I know this is not part of your experience. We had cassette tapes. And we, okay, if you're down with this. So we would go to the store and we'd buy cassette tapes so we could like record something off the radio and play it back ad nauseum, right? Or I had a double deck cassette player. So I could put my friend's tape in one and put my tape in the other and directly copy. And then I would have a duplicate of their tape and I could, yeah. So when we went to buy the tapes, they would have things like CRO++ or something like that. And I was like, I wonder what in the world that means. I don't know, this one's cheaper. This one's more expensive. This one's in the middle. Probably the one in the middle is the best dollar for, I had no idea. But what they're doing with those tapes is you have a gel. So here's your substrate. Here's a gel. And in that gel, they have a bunch of tiny little, let's call them bar magnets, made out of that stuff like the chromium oxide. And so to record information on the tape, you take a magnet and you put the magnet over the tape, just a small little magnet they make is a little electromagnet. And you put it over the tape, and because it's a gel, those little magnets will rotate because of the force, just like we saw the interaction with the force here. And then you take the magnet away, and the gel holds them in place. So now you have a magnetic field that's been produced on the tape by making those little things rotate. And so you change the magnetic field up, down, whatever. And that's how the information is recorded. Then to play back the tape, you just run the tape over something that measures the magnetic field, and you get back the information. It's kind of cool, right? Now, I know you guys don't know all this stuff, but I have to talk about it because it's so cool. Back in the day, when our computers crashed, it would flash on the screen core dump, and then it would run through a bunch of numbers. And over time, I learned the core dump is where it is writing the memory. So it was taking the values from each memory location and writing it to the hard drive. Then when I finally learned all my physics, I learned the history of this. They used to have memory for computers with magnetic cores. That is, you had a little piece of iron, and they would make the iron either have a magnetic field up or magnetic field down, and that's how they stored the memory. So it was magnetic field up, magnetic field down. And so the core dump was going through and reading the magnetic fields in all of those little cores to record the memory. These days, we still use this technology. Some of you did raise your hands with the cassette tapes, which shocks me because I haven't used even a VCR, which is the same technology, in more than a decade. But these days, I'll come back to that because it's so cool. These days we use, where is it? There we go. We use hard drives in our computers still. Now we're slowly moving away from hard drives to solid state devices. But a hard drive in a computer is the same idea as a cassette tape. You have those platters, which are just pieces of metal. And on the metal you have the gel, and in that gel you have the little magnetic particles, and you orient those particles. So the hard drives are storing information in magnetic fields. So you can see magnetism pervades a lot of what we do. Now I do have to say the solid state device that's using transistors, it's a completely different thing, it doesn't have magnetism in it. But you can destroy a hard drive or destroy the information on it if you bring it close to a magnet, because what's going to happen? It's going to change the orientation of the magnetic fields in the gel, and that's going to compromise your data. So that's why you never have a hard drive and put a magnet on it, right? It's not the smart thing to do. Okay, get back to where we were in the actual lecture. Ferromagnetism is not the only type of magnetism. Ferromagnetism is the strong type of magnetism. But we have two other types of magnetism here. We have paramagnetism. Paramagnetism has the same feature of magnetism. If you have something that's ferromagnetic and I bring a magnet nearby, it will be attracted. It doesn't matter if it's a north or a south pole, if it's ferromagnetic, it'll be attracted. Paramagnetic, if I bring a magnet close, it will be attracted, but much more weakly. So paramagnetism acts like ferromagnetism, except for it's very weak. And then there's diamagnetism. And diamagnetism is diametrically opposed. So if I bring a diamagnet close to a magnet, a diamagnetic material, close to a magnet, it will be repelled instead of attracted by the magnet. That seems bizarre to us because it's not part of our experience. And I'm not going to do it. If you go to this video on YouTube, you can watch video of this frog being levitated by magnetic fields. Because frogs, like humans, are a large percentage water. And water is diamagnetic. And so you put the frog in a strong magnetic field, and instead of being attracted, it's repelled. And so they put the strong magnet below the frog, and here's the frog, and it levitates. And of course, one of the concerns is, are we damaging the frog with this?
Oh.
You don't really know until you do it, but after they did it, they couldn't find anything to suggest it caused any harm to the frog. They didn't have anything to suggest it would, but you never know. Other experiments with animals involving magnetism. I just have to. So crabs, at least some kinds of crabs or lobsters, they know what direction is down because they have little grains of sand in these little things that basically the sand, because of gravity, will tell them what direction is down. And so scientists were like, I wonder if that's really what it is. Scientific method, you have to have it, their hypothesis is they can tell what direction is down because these little sand things. So they remove the sand things and replace them with little pieces of iron. Absence of magnetic field is going to behave the same. But if you put a magnet up on top, what's going to happen? They pull up. And so what did they do? Lobsters or crabs, whatever they were, they flipped over on their backs because the little pieces of iron were telling them that up was down. It's a great experiment, isn't it? And no animals were really harmed. I mean, these are the kind of people who eat animals anyway. I know. Some of you do too. From blood. Yeah. Mm-hmm. Okay. So 3 types of magnetism: paramagnetic, ferromagnetic, and diamagnetic. I'll put up here. All materials are at least one of these. In fact, all materials are diamagnetic. But diamagnetism is very, very weak. So if it's paramagnetic or ferromagnetic, that's what you're going to observe, not the diamagnetism. So you only observe the diamagnetism if it's not paramagnetic or ferromagnetic. So make sure, not for the test next week, but for the one coming after that you know the differences in these types of magnetism. Albeit the only type we're going to talk about is ferromagnetic. Now, what makes something magnetic? It comes down to quantum mechanics and the angular momentum of the protons and neutrons and electrons and the electron orbitals. All of those things play together to give you the magnetic behavior. What do we usually call, what's the name we use for the magnetic moment for an electron? It's something that you all know. The spin. The spin of an electron is telling you about its magnetic moment. It's telling you about its magnetic behavior. People thought when they first measured the magnetic behavior of electrons that they must be spinning to give them that magnetic behavior, and thus they called it the spin. We now know that is physically impossible. The electrons cannot be spinning to create this magnetic moment. But we still call it spin. Now let's take this. This here is a compass. Come back to Chad's desk again, even though it's here. We have the compass. It has a needle. One side is marked N, it points toward Chad. One's marked S, and it points toward Leslie. That kind of sounds like a sound observation, but I think you all know if I had to switch places, that the needle wouldn't change. So the N is pointing to, as we said, the north magnetic pole, or not north magnetic pole, the north geographic pole. If I take this R magnet, which I think I set up correctly, and I bring it out here, it has marked south and north, so I'm going to put the south end close to this, and the one there that's marked N is attracted to it. That establishes our basic opposites attract. And if I flip this around, that's going to flip too, so opposites attract. So I take this away. It's the Earth's magnetic field now that's responding to, and it tells us what direction the magnetic field lines here are pointing. Now, something that you probably are unaware of, I did mention that the Earth's north magnetic pole is moving, the south magnetic pole are moving. But one thing you're maybe not so aware of is the magnetic field lines. When we looked at the picture, we saw coming out of the north pole, which is the north magnetic pole, which is the south pole, and then coming around to the north. But the sun interacts with those magnetic field lines. And so do certain features of the Earth, like we have iron in the rock. So the magnetic field lines don't just make straight lines, they do some curving. And the sun will cause the magnetic field lines to deviate. So your compass will actually vary throughout the day because of the directions of the sun changing as the Earth rotates. And it will deviate differently depending where you are. So if, for instance, you're a pilot or a mariner, you actually need to have a chart to tell you what direction the magnetic field lines are pointing in different locations so you can use a magnet for navigating. Now, my picture up there says that this is made up of little domains. A magnet can be broken up into small little pieces that each behave as their own magnet. And in general, those should be just random. If they're randomly oriented, if all the little magnets are pointing random different directions, then the overall magnetic field is just going to add up to 0, right? You add as much in this direction as this direction, you add the fields as vectors, it adds up to 0. But to make a permanent magnet, you have to get those aligned. There are two ways of doing it. One is to have magnetically soft materials like this. Magnetically soft means even though this is a solid rod, I can rotate those little magnetic domains. I can rotate it using a strong magnetic field such as this creates. So I'm going to take this and I'm going to put it in backward. I need to rewrite this, but it says insert north here, insert south there. Well, I'm going to insert north where it says insert south. Put this to complete a loop. So magnetic field lines, remember magnetic field lines always do a loop. And I press my button to make the strong magnetic field. And now I'm going to take this and do the same thing I did before. I'm going to point the south end toward the magnet here. And now the south was attracted. This didn't change, so what I did is I just changed the poles on this. I made the north-south and south-north. I've rotated. You obviously didn't see any change in this magnet when I did it, but I rotated those little domains in it so that it behaved oppositely. Now I'm going to fix it so next time I use this I don't get confused like, what in the world? So I just make strong magnetic field here, and now it's realigned. I'll bring it up, put south here, and if I did realign it, now the north comes around as attracted to it. So you can take something that is magnetically soft, that's ferromagnetic, and make it into a magnet by making it putting strong magnetic field. Something that's magnetically hard, where it's hard for those things to rotate, take something more. You have to heat it up to make it magnetically soft. And so you take a piece of metal and you raise it to what's called the Curie temperature. The Curie temperature is the temperature where the magnetic domains are free to rotate. Still a solid, not the melting temperature, but magnetic domains are free to rotate. Then you put an external magnetic field, and they're all going to line up so that magnetic field lines go out of north and come into south. And then you cool it below the Curie temperature, and you have a permanent magnet. So that's how these things are made to have their magnetic orientations. Yeah.
So what do you describe as a permanent magnet then?
So a permanent magnet is something that's relatively hard so that the magnetic domains won't easily change direction. So my magnets aren't very permanent. These here, yeah, these are much more magnetically hard. They're also pretty strong. So if I take this, now this is not shaped the same, right? So what direction is what? You know, what's north, what's south? I think that it's probably, yeah, it doesn't matter how high or low I put it or how I rotate it. So I have like north on this side, south on this side, well, backward. North on this side, south on that side. So this has the poles at the top and bottom, whereas this has the poles left and right. You can make magnets in all kinds of crazy shapes. You're just going to have the magnetic domains curving with whatever you put in. Yes?
So if you heat something up above the Curie point, is it non-magnetic at that point? Or?
At that point, it has no permanent magnetic field, which means that the Earth's magnetic field is weak, and it will probably have a weak field because of the Earth's magnetic field, but it would be not very strong. If you put in a strong magnet, then they'd all line and you'd have strong.
Okay, but like if you stuck a magnet to it, would it?
It would become, yeah.
Okay.
Yeah, if you stuck a magnet, they would all align and it would be sticky. Okay, so that's the physical nature of magnets, how they are physically constructed. Something else you'll notice is the domain size has changed. As you get things to align, you can get the domains to merge together, or you can cause them to fracture as well. Okay, so there's, for iron, the Curie temperature around 770 Celsius. And yeah, I'm just going to move forward. I don't even want to talk about this yet. I'll talk about this part here in a later lecture. I'll talk about it later. What kind of magnetism is always present in materials? Diamagnetism is always present. Diamagnetism is you bring a magnet nearby and it's repelled. We don't ever see that because it's very, very weak. Paramagnetism is a weak form of ferromagnetism, but both are stronger than diamagnetism. So if it's paramagnetic or ferromagnetic, we're going to see that, and the diamagnetism is so weak that you really have to have a super strong magnetic field to observe something. So which one's the strongest? Ferro, which is why we talk about it. Which is always repulsive? Dia, right. Suppose I should have circled ferro when you said it here. All right, now we're ready to talk about the bulk of what we're going to do with magnets. It's a force field, so calculating the force from it. So here's the equation for the force when I have a charged particle Q going through a magnetic field of strength B with a velocity vector V. And when you read that equation, you have the cross product. You hopefully remember using cross products in this class. Cross products is multiplying the perpendicular components and getting a direction that's perpendicular to both of the original vectors. So let's take an example. Let us say that I have a magnetic field. Well, we're here at the Earth. Magnetic field lines are going that direction. They're going north. So I have a magnetic field that's going that direction. If I have a particle that is traveling this direction, so its velocity is that direction, and it has a positive charge. I choose a positive charge to make our life easy for the first example. So we have magnetic field is north, the velocity is west. What direction is the force going to be? Can anybody lead us through in determining that? If not, I will do it, but I'm just asking for... Nope. You confident enough, Sarah? No. Okay, so Q is positive, north, south, west, east. And we have the magnetic field is going that direction, and we have the velocity is going that direction. And our equation that we just saw for the first time ever is force vector is equal to Q V vector cross B vector. It's very important to have the vector signs here. Without the vector signs, it's a multiplication instead of a cross product. It means different things, you get a different answer. So, right-hand rule. You always take your right hand, sorry to my left-handed contingent, but it makes life easier for you. Take your index finger and point your index finger in the direction of the first vector in the cross product. So since it's Q V cross B, V is the first vector. And then I take my middle finger and orient my middle finger in the direction of the second vector in the cross product. And then my answer, is the direction my thumb points if my thumb is perpendicular to both the index and middle fingers. So not the test that you're having next week, but the following one, you're definitely going to have to do this. So you need to be able to follow through and do it. So I'm going to take my right hand. The first item was the index finger, that's velocity, pointing that direction. So I have my index finger pointing to your left. And then I need to keep my index finger pointing that direction, orient my hand, so I can make my middle finger point the direction north, and then my thumb points into the screen. And so the direction of V cross V is into the screen. Now, notice how it's kind of hard to get your hand in the right direction. Keep in mind when you're doing it on a test, you can rotate the paper as appropriate, so you don't have to be like that. Right? You don't have that option when it's on the screen per se, but on the test you can, so you don't need to contort yourself on the test. So what we ended up with going into the screen. How do I indicate a vector into the screen?
It's perpendicular.
Because it occurs so often, we put a circle with an X in it. That X is to indicate an arrow that you're seeing going away from you. So since arrows have fletchings on the end, that X is to represent the fletchings on the arrow, the feathers. So that's how we indicate the force is going away from us. Just as a guess, how then would they indicate coming toward us? Yes. So circle with a dot for the point of the arrow is coming out. Circle with an X is going away. So you're going to see pictures like that, and you need to be able to interpret them, right? Rather than just be confused and like, well, I can't do this. Don't know what the symbols mean. So we did this for a positive charge. What would happen with the force if it was a negative charge? If it's a negative charge, the V cross B is going to stay the same. What happens if I multiply my direction by a negative sign? Opposite direction. So if it had been a negative charge, then my right-hand rule says into the page, and then I have to reverse the direction because it's negative into the page. So you have to be aware of these things. You have to think them through carefully. Otherwise, you're bound to make mistakes. Obviously, 2 mistakes may turn out to give you the right answer, but we want you to understand. Leslie?
So, negative to the screen or just switches to the other direction?
Negative sign means it's going to switch direction.
Yeah, so if it's going into, then it'll be out.
Right. And if it was out, they would put it in. Yeah.
So charge, like negative charge, just doesn't attract to north or south.
Correct. Correct. Electric charge is not attracted or repelled by a magnet. It's only if it's moving. And if it's moving, then this gives us the force. So that's kind of, they're different, well, we say they're different forces. Actually, we combine them. Electricity, magnetism are combined as to one. But for our purposes, we think of it as completely separate forces. So yeah, you put a magnetic field and you put a charge here, it's not going to have that force caused by it. Now this was an example with the velocity perpendicular to the magnetic field. What would happen if instead I had the velocity like this? What then? Cross product is multiplying perpendicular parts. That's why we have the cross, to remind us of the perpendicular. So if they're parallel, how much is perpendicular? 0 by definition. Hence, your force would be 0 if the velocity is parallel or anti-parallel to the magnetic field. You have to have a perpendicular component for it to have the force. So that actually brings up an interesting. I actually had this question on my prelim exams to get into the PhD program. well, a variation of this. If you have electric field lines, this was actually the starting part of the question, but if you have electric field lines that are going, or magnetic field, they're going like this. B is our symbol for magnetic field lines. And you have a particle that comes in with a velocity like this, what's going to happen? First of all, you know that the force is going to be perpendicular to the velocity, right? So if the force is perpendicular to the velocity, it cannot speed it up or slow it down. It can only change its direction. And so the particle is going to stay going the same speed, parallel to the magnetic field line, but it's going to be curved because of this force and end up doing a circle, so it'll spiral around the magnetic field lines. That was the beginning part of the prelim question. Then it was like, how could you use this to make a microscope? Okay, what if the angle is not 90 degrees or 0? Then you find the perpendicular component using trigonometry. Actually, I have a picture. I don't know where I have the picture. I'll draw it here. If I have, here's the magnetic field direction, and here's the velocity vector, then the amount that's perpendicular is going to be v opposite side, so sine theta. And so the perpendicular part of the velocity to b is v sine theta. And so the magnitude is going to be b times sine theta for the cross product. So the magnitude is calculated here. Notice there's vector signs are dropped. The force for magnetism is qvb sine theta. The sine theta is there to give you just the perpendicular components. So when you actually do problems with magnetic force on a moving particle, you want to start with find the magnitude first, and then 2, use the right-hand rule to find the direction. So just do the 2 as 2 separate pieces and put them together to get the vector that has the direction and the magnitude. So my next slides are things about how this works. First of all, A cross B is not equal to B cross A. Why? Because if you had A cross B, A would be the index finger and B would be the middle finger. If you had B cross A, you would reverse those. And so you'd have to reverse your whole hand. So B cross A is minus A cross B. You can't just take one vector and put it in the index finger direction, one vector in the middle finger direction, and call it good. It has to be the first one is the index finger, the second one is the middle finger. Okay, another thing that we went over first semester, but it's important to review. If the vectors are like 30 degrees from each other, I'm still going to put my index finger in the direction of the first one, so that's B. And then I'm going to make my middle finger so it bends somewhere between, straight with my index finger, and going back opposite to it. So my fingers have to be somewhere between there for the second one. You do not hyperextend to make your middle finger go back behind your index finger. You also don't do more than 90 degrees to make it go through your palm. Or more than 180, excuse me, make it go through your palm. So you have to have the angle is between going straight with your index or going opposite it in the direction of your palm. Because I have seen people who did it like this, and that's going to give you the wrong direction. Which hand do you use? The right hand, because I've seen people use the left hand, not that they didn't know what they were doing, but that they forgot that it was important. And if you forget it's important, well, you make mistakes. Yeah, this is just illustrating what we've done. Illustrating wrong way to do it because, everybody wants to see the wrong way. And yeah, here's the picture I was showing for the perpendiculars. Okay, units. Remember I said the Tesla is the unit for magnetic field. And I said we'll worry about what the Tesla actually means later. Here's where that later is. We have the equation that said magnetic force QVB sine theta. I wrote it this way just to avoid a vector sign. So that means the units of B can be calculated. So what are the units of force? Newtons, right. I was like, I know everyone in the classroom knows the answer. So what are the units of charge? Coulombs. And what are the units of velocity? How about the units for sine theta? None. No, the angle would be radians, which is none, but
That's the way we don't have a
yeah,
unit.
yeah. So a Tesla can be written as a Newton per Coulomb meter per second, or a Newton second per Coulomb meter, or a Newton per meter ampere, because the ampere is a Coulomb per second. So those are all different ways of writing the unit for a Tesla. So now we can relate the Tesla to the fundamental basic units. The last one I wrote is still not fundamental because newtons are not fundamental. So here is the fundamental. Kilogram meter per second squared divided by meter ampere. Cancel those meters. Equals kilogram per ampere second squared. That would be the unit of the Tesla in base units, because the ampere is the fundamental one. The Coulomb is considered a derived unit. Probably none of us care. But it is important to have it laid out there that there is a meaning to the Tesla, that it's not just, something made up. Something similar, I suppose, I should have done was a farad. What do we measure in farads? Starts with K, yes. Capacitance. Capacitance is measured in farads. And so we have equations like Q equals VC. So that means C is Q over V. This is actually the definition here. So the unit is going to be Coulomb per volt, which is joule per Coulomb, or Coulomb squared per joule. And then if you want to get to fundamentals, you have to replace the joule with a Coulomb squared per kilogram meter squared per second squared. So that's a Coulomb squared second squared over kilogram meter squared. But Coulomb's not fundamental. Ampere is. So that's ampere squared second to the fourth over kilogram meter squared. That's what a farad is. I just feel a lot more comfortable putting F than putting all that mess. And then we'll learn about the Henry soon enough. A second unit for magnetic field that you will see a lot, the Gauss. The Gauss is simply a Tesla divided by 10,000. So one Gauss I think capital G is what we use for it. I never use Gauss personally, so that's why I say I think, is equal to 10 to the minus 4 Teslas. We use that because magnetic fields tend to be small, and so we can talk about the Earth's magnetic field as 0.5 Gauss, and it makes it so it's a more reasonable number to talk about in that unit. So those are the two units that we'll have for magnetic field. No other ones. We don't have some crazy American version of unit for magnetic field. Good to know, right? Makes life a little easier. I've already talked this one out. Problem-solving techniques. Let us say that you want to do a homework problem. God forbid. You have a homework problem and it says, you have a particle, has this speed, in this magnetic field, what's the force? So here's some steps. First, the magnetic field is going to be 0 if the velocity is 0, right? Going back to the question that Wes asked. If velocity is 0, magnetic field is going to be 0. If the magnetic field velocity is parallel to the, magnetic field velocity. If the particle's velocity is parallel to the magnetic field, again, there's going to be 0 force. And of course, if the particle has no charge, there's going to be no force. So, or if the magnetic field is 0, I don't have the no charge up there, do I? Yeah, because it says on a point charge. So, but I actually should have put a fourth one there. If the charge is 0, there's no force. So always go through those first, right? Because that's really easy. You can say, oh, the force is 0, I'm done. Then we have what to do if the force isn't 0. Determine the angle between the magnetic field and the velocity. From that, then calculate the magnitude. Q times B times sine of that angle between them. And then finally use the right-hand rule to determine the direction. Are those steps simple or hard? They're simple. Of course, putting them into practice may not be simple, but the steps are simple. So let's first practice the right-hand rule. A positive charge travels east. So I'm going to draw pictures here just to north, south, east, west. So we have a positive charge travels east. That's not east. That'll do her. So our velocity is like that, and the magnetic field points down. How do I make the magnetic field point down? That's how we draw for the magnetic field pointing down. Up would be out of the screen, down would be into the screen. So, with that, notice that it is a positive charge. That's important. What direction is the force? Okay, we have answers from a number of students. Let's do a voice vote. How many people say it's up?
Oh, you said voice vote. I do.
How many people say the force is down? How many people say the force is east? How many people say the force is west? How many people say the force is north? One?
Is up north?
Yeah.
No, up is going to be out of the screen. Right down
yeah,
into the screen.
okay. My vote goes to north.
Yeah.
Okay, so back to north. And how many people say north? 1, 2, 3, 4, 5, 6. Are you going to say this, Ryan?
Yes.
7, 8. Okay, I'm going to put 8 there. How many people say south?
I do.
Well, I'm going to count Andrew and Wes. Okay, so we're learning here. Don't feel bad if you're in the wrong camp. I haven't done it yet myself, but we're going to do it together here just to make sure we all now can do it now that everybody's taking a shot at it. So I take my right hand, not the left, and I point my index finger in the direction of the first item, which is V. So my index finger is pointing that way. Then I orient my hand so I can make my middle finger point into the screen. And my thumb is pointing in the north direction.
I got the magnetic field and the force.
But it's easy to make mistakes. It's good to practice. That's why we're doing the practice here. And once again, don't feel bad if you're wrong. Feel bad if you didn't think it through and we're just like, well, let's see what he says. So, the correct answer was north. And I am glad that Ryan, who was very vocal in his answer, also was able to realize before we got there, oh, I misinterpreted what direction was did the problem right, misinterpreted direction, right?
Is that going to be the standard? Like down is away and up is to us?
Yeah, the standard will be up is out of this page, down is into the page.
Okay.
I mean, there may be some problems where you don't, but that's usually the standard. Okay, now we have the charges traveling east, magnetic field points down. That is the same as we had here. So all that has changed is it's a negative charge. South. South, because if it's a negative charge, you reverse the direction that you got with the right hand rule. I know I could have been tricky and I could have asked this one first, and at least half the class would have had it wrong because they would have forgotten to reverse the direction. You do the right hand rule, you get it done, and you're proud.
Of course, is the mental construct, so A.
Okay. Okay, I think I have one more yet. A positive charge travels east in a region where the magnetic field points east. What direction is the force on this charge? All right, people are getting the hang of this. No force. Why is there no force? They're parallel, right? That was our first thing. Look at those cases that give you zeros. Okay, so doing an actual problem. Suppose a proton is moving straight down directly toward the equator. And so it's pictured here. Protons moving like that. So you have the magnetic field is going, I'm going to draw it here just so we're real clear. There's the magnetic field direction. The velocity is shown. Over here is a diagram to make it extra clear. What is the direction of the magnetic force on the proton due to the Earth's magnetic field? So this is a real problem. This is something that is important to our life on Earth, as I mentioned at the very end of the last class period.
Down. Wait, up and down and sideways is west, right?
Okay, so we have velocity is in, magnetic field is up, so the thumb should be pointing into the page. And the way this is shown, east is into the page. So I would have gone with into the page, whatever that means, right? Because that's not quite as clear. So you have a force that's going into the page here, or what I believe to be east.
How do you know that was the east? I mean,
Because when we have north on top and south on the bottom, then we have east that direction and west that direction. And so as the Earth rotates, the east and west are going to rotate with it. And so you go to the side and east would be going that direction. Yeah, that's why, to be safe, I would have said into the page and then worked out from there. So we have the direction of the force. Explain how the Earth's magnetic field then is going to shield us from bombardment of cosmic rays. We have protons coming from the sun, lots of them. What happens to those protons when they hit our magnetic field?
They get shot into the thing.
They get shot east, right? And so that means they're not coming to us. What if they were electrons instead of protons? Because we have electrons coming too. They'll be shot west. So the charge is being shot out to the sides, which means that we don't have those charged particles coming through us. It's protecting us from that. Those charged particles, as we'll learn later in the semester, we call them ionizing radiation. And they can cause lots of damage with us. So they're protecting us from having mutations and growing third eyes or whatnot. Well, obviously, you know that's a joke. That's obvious. What if nope, don't have it. What if that same proton was coming here? Let me move it a little so I moved it a little so it wouldn't be parallel. So what happens there?
We're talking proton or electron?
Proton. Your V is the same direction, but now your B, instead of being up, it's going to be like that. So it's still to the side. It's going to be less force, right? Because you have the sine theta in there. But in this case, it's going to make, as it moves sideways, that sideways velocity then is going to be perpendicular to the magnetic field. and it's going to make it spiral around that magnetic field line and make it come into the Earth's atmosphere. So these solar wind particles actually come into the Earth's atmosphere near the poles because the magnetic field lines guide them in. They're not perpendicular to the surface. They're now somewhat coming in and guide them in. So that's why northern lights and southern lights, aurora borealis and aurora australis, occur near the poles because that's where the magnetic field lines are coming into the Earth's atmosphere. Okay, we're out of time. Have a great Sabbath. I hit hide instead of stop. Yes.
Do you have the